There we go. Okay, all right, we're ready. All right. Good afternoon, everyone. Thank you for coming to the seminar. So I want to start with the acknowledgement of country. I want to welcome any Torres Strait Islander or Aboriginal people in the audience, and also to recognize that the contributions of the longest continuous culture here in Australia, and we are here on the lands of the Ngunnawal and Ngambri peoples, and we want to pay their respects to those people, the elders, past, present, and emerging. And so it's my great honor to introduce Elle, who's coming from Victoria University, Wellington. She did her Master's of Natural Science at Cambridge University, and then I learned that she actually did a project with Mark Hoggard here in the audience, which I didn't know until until last week or so. And then she did her PhD at Victoria University of Wellington, and she finished her PhD last year. And then since that time, she's now a postdoctoral scholar. And so I am very happy to hear and learn more about Taupō and seismicity, and also some of the engagement with the local people. Thank you.
Yeah. Kia ora. As Megan said, I'm Elle. I'm a postdoctoral research fellow at Te Rangawaka, Victoria University of Wellington. I'm originally from the UK. I was born in Devon in the UK, and I came to New Zealand in 2019 for my PhD. And I'm here today to talk about that work focused on this beautiful place. This is Taupō. This is Lake Taupō, which is the lake above Taupō volcano, which is an active caldera volcano in the central North Island of New Zealand. It's an area of great intergenerational importance to the people of Aotearoa New Zealand. And any research that we do on the volcano is in particular relevant to the indigenous Māori iwi communities around Taupō. So iwi is a word for tribal group. And in particular, it's for Taupō, that involves Ngāti Tuwharato, which is the iwi within whose rohe or region Taupō lies. Words here sound so different. So this work is not just my work. It's many different colleagues who I've partnered with, my supervisors, and many other people and colleagues, partners from the central North Island. Is this going to work, or is it going to? No, it's not. All right. We've got some pictures here of some colleagues. So Finnels Kemp, Martha Savage, and Colin Wilson, as well as Bub Smith, Kelvin Tapuke, Lucy, Ian, David, Kate Morihuho, so many people from Victoria University, from the Eclipse program, which is this logo here that was a part of a large transdisciplinary, trans-institutional 5-year large research program focused on the caldera volcanoes in Aotearoa. And also colleagues from the central North Island and around Taupō. So I'm going to talk a little bit, focusing a lot on what we know about Taupō, thinking about the seismometer network we put out, in particular the co-production approach we took to deploying that seismometer network, and then thinking about what we can learn from the seismicity at Taupō and how we can improve our knowledge of the volcano. It's going to be relatively light on seismology detail. So if you want the more seismology heavy version, you'll have to come to the talk tomorrow. Taupō lies within the Taupō volcanic zone. This is the on-land extension of the Kermadec arc. It results from the subduction of the Pacific plate beneath the Australian plate, which is the North Island of New Zealand, you can see in this picture. And basically the Hikurangi Plateau that is subducting is anomalously thick. It's subducting, it's releasing fluids that move upwards through the mantle wedge, and they are causing very, very high amounts of mantle melting. The topovolcanic zone is the most productive silicic system in the world. There have been 4 supereruptions in the last 2 million years, and it's also kicking out vast quantities of heat. There are lots of geothermal systems there. So the topovolcanic zone itself, it extends from the Bay of Plenty in the north to just south of Ruapehu in the south. It's clearly really segmented along strikes. So in the north and in the south, there are andesitic cone volcanoes. So Ruapehu and Tongariro in the south, and in the north, Whakaari, White Island, where there was the tragic loss of life during the eruption in 2019, and there are eruptions going on there currently. In the middle, though, it's rhyolitic. So the central TVZ region, here between Taupō in the south and Ōruanui in the north, those are the 2 active caldera volcanoes that we have, but there are lots of old calderas in between. So there's lots of evidence for volcano-tectonic interactions in this area. In particular, there's a rift system running through the area. So the Taupō rift, it's spreading about 5 millimeters a year just south of Taupō, up to 15 millimeters a year in the north. And evidence of volcanic tectonic interactions we've got on sort of a long-term, tens of thousands of years. When Taupō is active, in the rock record, in the eruption history, when Taupō is active, Ōruanui is not. And when Ōruanui is active, Taupō is not, despite the fact they've got different magma systems and they're 80 kilometers apart from each other. They're also it's connected more broadly to the tectonic system around. Jesse Schuler, a master's student in our department, found an effect of the Kaikoura earthquake that happened in 2016 in the South Island, having an effect on Taupō. And we're also actively looking into the relationship between slow slip events on the Hikurangi subduction margin and activity in the Taupō volcanic zone above. So the most recent supereruption was Ōruanui. It formed Taupō caldera as we know it today. And that was 25,500 years ago, and it produced 530 cubic kilometers of rock. There have been 28 eruptions since Ōruanui. This map here shows the collapse structure in blue. In particular, we have here this structural caldera. This is mapped from a gravity low, where basically there's missing rock. This is the area of the old magma system that collapsed during the Ōruanui eruption. And then all of these dots here, these are the origin sites, the vent sites for the 28 eruptions since Ōruanui. You can see that they form this sort of rift-aligned lineament. So we've got tectonic control on at least shallow magma pathways. The largest and most recent eruption was the Taupō eruption that happened about 1,800 years ago, and that's that red outline, further collapsed the caldera. Taupō volcano is still active. We see unrest on approximately a decadal timescale. So we see periods where there's an increase in seismicity, and also we see lots of ground deformation. There's also some evidence historically of hydrothermal unrest. Possibly there are geochemical signals as well, but because there's a massive lake on top, it's really hard to tell what's happening beneath it, particularly telling what is even the base background level and what's varying. So approximately every decade we see activity at Taupō. Most recently, there was some in 2008, and there was some in 2019, and there was some in 2022 to 2023. And we see these sort of broad 2 patterns. We see activity north of the lake in the Taupō fault belt, An example of this is 2001. This is some work looking at those earthquakes from a master's student in our department. Lots and lots of earthquakes all happening on these different faults, and also a little bit of seismicity here in Western Bay. So we saw activity like this in 1922, in 1983, and also in 2001. The other place we see unrest is beneath the lake itself. So this is, these are the earthquakes from the 2019 unrest episode. But this sort of activity also happened in the 1960s, in 1983, in 2008. In 2019, we saw this pattern of seismicity, and then in 2022 and 2023, we also saw earthquakes. We also see ground deformation, asymmetric ground deformation, often with this 2001 type asymmetric across the fault belt deformation, whereas we get uplift under the lake during this beneath the lake earthquakes situation. It can have quite serious consequences. So these are a load of pictures from different unrest episodes, landslides, deformation. These people now have a lovely lakeside property. They did not have a lakeside property before the earthquake. We've also got 2019. This is some damage to some wastewater pipes that spilt a lot of waste into the lake, and that was probably related. They broke 20 years into their theoretically 100-year lifespan, and it's probably because there was a lot of uplift and ground deformation happening. Finally, in 2022, these are some mappings of the deposits left after a tsunami in the lake. So there was a magnitude 5.7 earthquake, very large, caused thousands of aftershocks. And also there was a couple of tsunamis, and there was a tsunami that went the whole way around the lake, and then this region here collapsed, slid into the lake, and caused another small tsunami in the bay that Taupō town is in. So that's the 2019 and the 2022 unrest. The earthquakes I looked at for my PhD were between those two unrest episodes and a little bit extending into the start of the 2022 unrest. Since it's active, 2020, sorry. The 2022 to 2023 unrest was sufficiently large that it was the first time that the volcanic alert level was raised to level 1. So this is Aotearoa New Zealand volcanic alert level. Level 1 means minor unrest. Level 2 is moderate unrest. Level 3 is it's erupting right now. And then it goes upwards from there. So I'll talk a little bit more about this and the work I had involved with this later in the talk. So we monitor the volcano. We have geodetic monitoring, and we have seismic monitoring. Geodetically, continuous GNSS sites, and also some campaign GNSS sites as well. And then lake leveling sites. So 4 times a year, they'll go and measure the level of the lake, and it's basically using the lake like a giant spirit level, seeing which parts of the ground around the lake are moving up or down. And this is a data set that started in 1972 and has been continuous since then. So it's a really long-term record. Seismic wise, we've got broadband instrumentation, we've got strong motion sensors, and we've got short period sensors as well. The thing is that the lake prevents dense instrumentation within it. So we've got no seismic monitoring, and we have one continuous GNSS sensor on Ōruanui Reefs, which is the site of the post-eruptive dome of the most recent eruption 1800 years ago. There's also 24/7 geohazard monitoring. The National Geohazard Monitoring Centre monitors for earthquakes across Aotearoa all the time. At Taupō, it's a really good starting point of a seismic catalogue, but it doesn't necessarily give us the level of detail that we'd like. It uses an Earth average velocity model, and it's very focused on those larger seismic events that are actually possibly a geohazard themselves, rather than telling us about the volcano. We've also got that limited station coverage. So the aim of my work is to try and better understand the magma reservoir beneath Taupō, so that when activity happens, potential future unrest or eruption, we can look at the signals that we're seeing, better interpret what's happening. So what do we know about where the magma is at the moment? Well, we've got evidence of where there have been previous eruptions. We've got the collapse structures and this structural caldera, this gravity low. We've also got the vent sites from the previous eruptions, and those match well in this sort of northeast part of the lake. Those match well with what we're seeing with seismicity, where we see earthquakes in this northeast part of the lake. Depth-wise, from geochemical analyses of past eruptive products, we're seeing the magma system that's sort of 5 to 15 kilometers depth, but mainly the rocks that are coming out the top have sat in the magma system at 8 to 12 kilometers and evolved. So the idea is we're wanting to improve monitoring for and response to future unrest and eruption. And there's sort of 3 parts of this. Working in partnership with local people. Tangata Whenua means local people. And thinking then about the geometry and the state of the magma reservoir and the processes that are causing that seismicity. The issue with a system like Taupō is that they exist on a massive range of timescales, upwards of tens and thousands of years for those largest eruptions, down to decades or days for, or even hours for system priming and ascent to eruption. And since we've not observed an eruption, it's really difficult to tell what's non-eruptive unrest and what's pre-eruptive unrest. So we really want to increase our understanding there. Unfortunately, we can't do that effectively without the collaboration between affected communities, emergency management, physical and social scientists all working together. Those relationships and trust between different communities of people are really crucial for translating any scientific understanding to improved resilience, and also making sure that the science that we're doing is relevant and useful for the people who actually want to use it. So I work with seismological data. And so a big part of my research has been putting out a seismic network, but working in partnership with local Māori, iwi, and hapu. So iwi is the tribal groups, and hapu is tribal groups. So working with them during the planning, deployment, and managing of this seismometer network. So the seismometer network here, the eclipse sites are shown in red. And then it's stretching further than that into the design of the project, right back from the very beginning of the start of the Eclipse research program, before the money was even applied for. Those relationships already existed, and we had people from those communities built in when they were planning the project. They were part of the project. So this map here shows the land information New Zealand, like the property tiles. So all the different areas all owned by different people. And then the yellow squares are the marae, so the traditional meeting houses. And each one of these will relate to a different hapu. So it's a very complicated area with lots and lots of people to talk to. So this co-produced approach to research, the idea is partnering with the people and communities that are affected by the research to do the research. It means those community voices are respected and represented, and the results of the research are useful and relevant you've built those trust and relationships into the future, perhaps leading to more research, and you're building that shared understanding. This approach is pretty atypical in geophysical network deployment, I think, and in volcano-related studies in Aotearoa, New Zealand. So after we'd done this this network, and after we'd removed it, we sat down and had some semi-structured like group discussions where the participants, so those were members of the research team, iwi researchers, emergency managers, social and physical scientists, we all got together and had a discussion about how our team had worked together, what worked, what didn't work, and how we went about creating and holding that space for the ability to co-produce that research. I thought I'd give you a bit of a taste about what that actually means in practice. So here are some fun pictures of field work. So having that, as I said, having that broad research team, having that community expertise, you can see all these different people involved in the project. We've got emergency managers, local experts and researchers. The idea was having all these different voices represented. It's going to improve the way that we did our research. So one example is the initial network planning. So we started off with a desktop exercise where we laid out like geology and the seismic, like what we wanted to image or measure, and then we thought about like what is the sort of scientific optimal, like what would we like to do, and then immediately started having those discussions about like what's possible, which areas are sacred or important, and which areas have access issues, which is going to work. We had that that adjusting with that local knowledge immediately. We then started communicating with iwi and hapu and Māori trusts about what we were doing. The idea is approaching the research in a respectful way where we're communicating about what we're doing, what our research is aiming to do, but also including their input as well. This also requires a lot of flexibility. It takes a long time, and you have to be pretty willing to be flexible about locations and timings, things like that. So attending meetings, going up and visiting when we were asked to, adhering to customs and protocol, the processes they want to set down, health and safety, really an important part when you're going to visit farms and working sites and things, as I'm sure you all know, but making sure that we're adhering to all of that stuff very carefully. We're showing that we're being respectful of their area. Also, I showed you that map of the marae and the of the land tiles. So we were making sure that we were asking the local hapu, even if it wasn't on their like privately owned land, so like officially legally in New Zealand law, there's the sort of colonial approach to like I bought this land and now I own it and I can do whatever I want with it, but also thinking more generally about what the rohe of the different hapu were, and then trying to respect those decisions that come back. So respecting, like, some sites we asked and the answer was no, so we just worked with that, found a different site, discussed with them if there was somewhere else that might work better, or in some cases just moved on to a different place. This involves a lot of communication, written documents about what we're doing that you can share. Also videos. This still is from a video that we made that a trust asked us to present what we've been doing. And also it would be quite common that we'd have people come with us to visit the sites, and I'd start explaining something to somebody And they'd be like, wait, and then it would be a phone in my face. And I'd have to explain it, and then it would be posted on Facebook so that people in the, well, more broadly in the community are able to see what it is that we're doing. These pictures are mainly from bringing landowners, students, both postgraduate and undergraduate students from our departments, and also more broadly bringing like school groups coming with us, and it really builds that like sense of ownership and sense of understanding of what we're doing. Those like face-to-face interactions are really key for like allowing people to ask questions, allowing that building of relationships, both amongst members of the research team, many of whom didn't know each other before the project started, but also having spent time discussing research and earthquakes and sharing that knowledge meant we could think about other projects in the future, and also building those relationships in peacetime as such meant that they could be leveraged in times of crisis. So when the 2022 unrest started, we'd built those relationships and that understanding, and we were able to leverage those to use them. As I say, this takes time. It's not easy to do, not least because of the academic and funding structures that are not really set up to do this sort of research. But it was really rewarding to go about doing it. It ended up a massive part of my PhD. I never expected to write a social science paper, but here we are. So it actually ended up like a full chapter of my PhD, and it's really shaped the way that I think about research, the way I want to go about doing research, the way I want to continue thinking about that in the future. So, earthquakes, seismology, yes. So this network that we put out is called the Eclipse Network. So the existing national GeoNet network, which is the permanent stations that exist, continuously monitoring and streaming data live out of them. These blue and orange triangles, those are all the, so the orange is broadband and the blue is short period instrumentation. And then the red earthquakes, the red triangles are the 14 broadband seismometer sites that we had out throughout the 2.5 years between October 2019 and May of 2022 that we had the instrumentation out. You can see that we're really increasing the density of stations close to the lake, in particular broadband instrumentation is a serious, was seriously lacking. So we really increased the number of stations there. And a recent GNS, which is the New Zealand, they're in charge of natural hazards monitoring and research. They're the Crown Research Institute that do that in New Zealand. They recently did a review that recommended 12 additional stations around Taupō. So we were enhancing, that happened after we'd put these sites in. But yeah, so adding these broadband seismometers installed around the lake, and once they're installed and recording data, we could start to analyze the data and see what we could learn about the volcano from it. So that's what we'll talk about now. So we're thinking about seismicity at Taupō. We're thinking about how it's related to the magma reservoir. If so, what can we learn about that seismicity, and what can it teach us about the modern magma reservoir and the processes that are happening within it? So mine is not the first analysis of seismicity. As I said, there's 24/7 monitoring that comes out near real time, analysis of seismicity by the GeoNet, by the National Geohazard Monitoring Center. And this is a really excellent resource for us who want to study seismicity in Aotearoa, but as I said, it would be nice if we could locate some seismicity with a specific velocity model for this area. And we also want to increase the number of detected earthquakes. So GeoNet only detects an earthquake if it is it passes an STA LTA threshold at it passes a particular threshold at 10 stations. So there are, as you can imagine, with this density of stations, there are lots of small earthquakes within the lake that get missed. So the other thing is more measurements will allow us to increase our ability to constrain depth. I don't know if you can see on this plot here, there's a lot of earthquakes conveniently at exactly 5 kilometers. This is because if GeoNet is calculating a depth, which is if you double that depth, if they haven't got a station within that distance to the earthquake, they'll operator assign a depth. So they are at 5, 1, 2, 3, 5, 12. They keep going down, but because most of the seismicity is shallow, we get this line of earthquakes of 5 kilometers, which we'd rather not have. So I analyzed the seismicity. At Taupō, I used a 1D velocity model that I inverted for using a program called Velest. We used machine learning based automatic picking and association techniques. They work quite well for this volcanic area, despite the fact that they weren't, they were trained on tectonic seismicity. And then we located the earthquakes to find maximum likelihood locations, and then used relative relocation techniques. So those use, how many of you are geophysicists? Anyway, using small differences in arrival times of similar earthquakes that are close to each other to reduce the amount of error in those locations, but only relative to each other. So it doesn't improve your absolute location, but it does bring into focus those structures that those earthquakes might be sitting on. We also inverted for local magnitude scales and calculated some selected focal mechanisms from first motion polarities. So here are those GeoNet earthquakes, and this is my final earthquake catalog. So there's 10,000 earthquakes in this. You can see that there's mainly seismicity along the rift, which is not a huge surprise. But we get lots of earthquakes happening along the rift, but so many earthquakes, we're just going to focus in on Taupō itself and see what we can learn about Taupō. So if we zoom in, we're seeing seismicity up here, swarms of seismicity all the way around the lake. These are colored by time, and the size is the magnitude of the earthquake. So we've got lots of earthquakes, 5,000 events over the 3 years that we're looking at here. And this is what they look like through time. So one thing to note in a move of, it's very irritating. So this dashed line here is when the 2022 unrest episode started. This is the start of May 2022. And this is when we took out all of our seismometers. We had to return them. We'd borrowed them from RSES in the US, and it had already been extended because of delays from COVID. So we had to return the seismometers, so we had to take them out, which is quite frustrating. But regardless of the fact that we reduced the number of seismometers, you can see there's a relatively continuous rate of earthquakes through time, and then there's a sharp jump in the number of earthquakes that we're seeing per unit time at the start of that unrest episode. So north of the lake, we've got these swarms of earthquakes. Lots of these are under geothermal power plants. So you see lots of seismicity continuously beneath those. But we also see swarms of seismicity where the swarms are sort of rift aligned, elongated in the rift aligned direction, and they also have focal mechanisms with a minimum compressive stress that's perpendicular to the rift. So it looks like they are rifting related, tectonically controlled earthquakes, and they have a relatively continuous rate of seismicity through time. Similarly, if we go to the southern part of this area, we've again got a relatively continuous rate of seismicity through time, and you're seeing these rift-aligned structures and focal mechanisms. We do also see some non-double couple focal mechanisms. They broadly have compressive regions in the same regions that the double couple ones have. So they're just sort of mostly a double couple mechanism with a little bit of a volume change, we think. So probably just geothermal fluids affecting the faulting. The story, however, is quite different if we go into the central part of the lake. So we've got lots and lots of earthquakes here. Particularly, they picked up in May of 2022 when the unrest started, and we'll look at those in some more detail now. So the main feature that we see in these earthquakes is that there is no tectonic looking control on them. The focal mechanisms are, I mean, it almost looks random. There's definitely no direct orientation of those focal mechanisms aligned with the rift. And we're also seeing particularly these features in the seismicity that are also not tectonically rift aligned. In particular, this arcuate shape in the seismicity. So I don't know if you can see this curve here. This is 3 slices through time. So this is everything before the unrest. This is the first month of the unrest. And then this is everything in the 4 months following that. So we have this curved shape in the seismicity. This is not an artifact of the location methodology. I did a lot of testing of swapping different parts of the methodology and seeing how it changed. It's visible both in the absolute locations and also in the relative relocations. It's also in the middle of our network, although it is in an area where we don't have any seismometers directly on top of it. It is one of the areas that is best constrained. It's consistent through time, through changes in the network and changes in parameter choices. So I'm pretty sure it's real. It's not rift aligned. It's not along any sort of rifting structure. It's not progressing through space, through time, like along, it's not propagating from like south to north or anything through time. And it's existing through that entire catalog, both before the unrest and during it, though it lit up in this first month. That's why I've separated it out. This first month of seismicity, it really lit up then. So the thing is, it is aligned with sort of the edge of this structural caldera. So other volcanoes do, like caldera volcanoes do show ring-shaped seismicity, both during unrest, like at Rabaul and Campo Flegueirai, and during caldera collapse as well at Barabunga, Sierra Negra. But these examples tend to have like a range in depths, like a curved surface, like a ring fault. Instead, these earthquakes have an incredibly consistent depth. They're all at 6 kilometers depth, plus or minus a kilometer. They're not flat in a sort of suspicious, there's a line in the velocity model way, but they are very consistent in depth. So we think what we're seeing is the intersection of a curved fault with a sub-horizontal structure within the magma reservoir. So that's pretty exciting. That's showing us some structure in the volcano that we haven't seen before, and we have all this seismicity happening through time. So we thought about research in partnership with Tangata Whenua, thinking about how we can work together to make sure that when we learn about the geometry and state of the magma reservoir and the processes that are causing the seismicity, that we're using that data in a way that is useful for people and including them in the research while we're doing it as well. I said I'd talk a little bit more about the volcanic alert level raise. So it's always useful. It's always nice to know that you've been useful. So throughout my PhD, this unrest episode was happening. And so I ended up presenting some of the preliminary versions of these results to the volcano monitoring group for discussion. Contributed to a conceptual model of Taupō that we can use to interpret activity based on what we knew at the time, and we keep building on it. And there was also a lot of discussion. Not all the people in the volcano monitoring group are seismologists. So it was good to be able to explain those areas where we know we have gaps in our knowledge. For example, talking about the poor constraints on earthquake depths. When you see just a dot on a cross section, sometimes it's easy to think of, to miss the idea that we've got like plus or minus 4 kilometers of error on this earthquake depth, and we don't really know where it is. That knowledge in itself is useful, but the communication and response to the science is also very important. So when this unrest happened, we'd spent 2 years building partnerships with people around Taupō, iwi representatives, farmers, landowners, emergency management, as well as people from within the monitoring group and from within GNet as a whole. And that was also 2 years of communicating with the public about Taupō more generally, as well as having lots of specific discussions with individual people. So when the alert level was raised, apart from a couple of rather dramatic news pieces from various ill-informed American and English news organizations, basically the response could have been panic. Oh my God, the super volcano, it's active. But it wasn't. And I think a lot of that was in part due to the communication strategy. We had a central document where we put in messages, questions that we've been asked by media so that we could put in and discuss those and come up with a sensible answer. So this, in a very practical sense as well, we put out a whole load of seismometer sites, and that meant that we basically tested which seismometer sites were the most useful for detecting seismicity. So this is what the network of seismometers and geodetic instrumentation looked like at Taupō in 2022. So once we've been doing the work, but before the magnitude 5.7 earthquake that shook everyone, had a tsunami, and freaked people out. And then this is what it looks like now. So you can see that there's been a massive increase in broadband instrumentation. Also, these 3 new sites, this one also has a broadband seismometer. It's just hidden by the strong motion. These sites are sites that were essentially eclipse sites. They're not entirely in exactly the same place, but these were the sites that were most effective during eclipse, and we were able to help with finding useful new sites to put instrumentation in. And this whole rounded impact was only possible because of the relationships that we built because of the co-production, most of these sites are on land that is iwi owned. So it was important to build those relationships up. And if I just sat and done my research in just done my seismology, sort of ignored everything else around it, I might have been able to contribute scientifically to that unrest response. But I think that the broader response was made possible because we all work together and talk to each other as well. So yeah, that's me. Thanks very much for listening.
Questions for Elle?
That's one.
Thank you for sharing your experience and also the scientific results. I was quite curious when you're talking with the UV tribe, what is sort of like the biggest motivating factor for them to sort of work together, and also maybe what is the biggest resistance?
I mean, I guess it will vary, right? They're not a single group, but I would say they care about what's happening in their area, on their land, what's going to affect them and their people. I would say one of the difficulties is there is a long legacy of negative experiences with scientists. There are times when you go to visit them and they're like, "Are you from GNS?" And you're like, "No." And they're like, "Oh, come in." There's a lot of trust difficulties. So that's why the relationship building sometimes takes a while. But generally my experience is people are really interested. They want to know, and they're also pretty well informed. They know what's happening. They just maybe don't think about it in terms of like seismology and P&S waves and where are the earthquakes happening. But they're always really interested to see like our perspective on what's happening. And you can talk to them about like, "Oh, did you feel that earthquake back then? Oh yeah, it was here. Look, this is your site. This is what the shaking looks like. And here are the other sites, and here's how we can like put all this together. Here's how it all connects together."
You mentioned the geothermal in the area. Are they actively pumping down or just pumping out? And does that affect the seismicity?
Yes. So it's hard to prove causality. What can I say? There is continuous. So these here, 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 and here, there are geothermal power plants. And these are the areas where there is continuous seismicity going on. There is also, if you look at INSAR data, there's a lot of subsidence. But there are also a lot of earthquakes that are not related to the geothermal system. Like this is an actively rifting area. Like
Are they monitoring as well?
probably. A little bit, yeah. So I'm sure there are people who within our department who have done PhDs looking at induced seismicity beneath Ngātamariki and Rotokawa, which are these areas here. And Bethany here is working looking at the Wairakei geothermal field, which is here, but expressly, contractually, not looking at induced seismicity. Yeah.
Yeah, on your next break.
you think it's gonna be possible to put another seismometer on the island there, since there's a GNS station? Has that been,
So
is there
there
a
are,
particular hurdle
sure,
for that
so,
one?
so this island,
Yeah.
there's only one island in the lake.
Yeah.
This is Mototoko Island. There will not be instrumentation on this
No.
ever. It's
But
it's
there's the
really,
GNS
really
GNS
sacred.
there?
Yeah. But
Nothing more.
so here there's Horomatangi Reefs, so it's not above the water, but it's the shallowest part of the lake that is so it's a dome from 1800 years ago, from just after the big explosive Taupō eruption. And basically there's a platform drilled into the top of it, and then there's a GNSS sensor on top of it. So that, I would say, that is a good contender for having seismic monitoring the lake. The lake is owned by Ngāti Whakato, so any instrumentation that's added need to be built in partnership with them.
Does anybody, sorry, any more questions? Has anybody investigated the use of mermaid seismometers?
I don't know. I have no
They're
idea.
floating seismometers,
Oh,
and so there's been, yes, in Princeton and others are leading this, and they have dumped them out into the oceans.
Hmm.
So you can imagine they only record P waves, but they just float, and then they transmit the data back, and so it's kind of a.
that's pretty cool.
Yeah, so maybe that would be something, because it's not going to, you obviously have to
Yeah.
get permission to do it, but it's not something that needs to be
Yeah.
permanent or could damage, or you need any to dig or to.
That's true. I would say that the lake is actively used for like water sports
Yeah,
and
that's
fishing and like all sorts. Yeah, also the lake bed is owned by Tūwharato, and so is the lake underwater.
Yeah.
There was a famous case where somebody tried to argue that they didn't own the lake, they only owned the lake bed, and they were like, oh, okay, then take the water out of it. Yeah, so they own the lake.
Again. Anybody interested in coming to dinner, please come see me. We haven't picked a spot yet, but we'll be figuring that out. If you want to come and join us for dinner.